杨汉，你不冷？我看你穿这样，我都觉得好冷。Today I'm going to talk about next section, rules of inference. Okay, so in this section you will see valid argument. Then we will see different inference rules for propositional logic and practical logic. And then we will see how we build arguments for statement. Okay, so let's see the Socrates example again. We have two premises. That means all men are mortal. Socrates is a man. Then we have the conclusion Socrates is mortal. So intuitively, this is correct because if all men are mortal, then Socrates is a man. So he is one instance within the man. And everything in this domain is mortal. Okay, so Socrates is a man. So and in this section, we will see how we draw conclusions from the given premises. Then we can verify the conclusion is true. Okay, so firstly, let's see the definition of argument. We can express premises and conclusions in this form. We list all premises above the line, and then we give the conclusion under the line. Because based on all these given premises, then we can get a conclusion. So then we call this the valid argument. Okay, so firstly, let's see what's the definition of valid argument. Okay, so previously we have learned conversational logic. So next, we will see different inference rules for two kinds of logic expression. Okay, let's see what's argument. Argument in positional logic is a sequence of propositions because we are trying to express something or trying to express a fact. Okay, so we have some proposition which is called premise and one is conclusion. So why we call that a series of propositions? If you consider the proposition is a sequence, so this is 1, 2, 3, then we have a sequence of propositions. We have premises, and the last one is conclusion. So once you give this, then we call that an argument because we are trying to argue something. We are trying to argue if we have the premises, we can draw a conclusion based on the given premises. So this leads to the next definition. If the argument is valid or not. Okay. So let's see the definition. What is valid argument? If the truth of all purposes implies that the conclusion is true, then we call this valid argument. So we have the propositions in the sequence, right? But we don't know the true force of that proposition. But here we assume all premises are true, then we can derive that conclusion is also true. Then we call this argument valid argument. Okay, so you can see the argument is not valid if you assumes all premises is true, but conclusion is false, then the argument is not valid. You cannot draw a conclusion based on the truth of all premises. Okay, so maybe we can see one example of argument. For example, we have the argument if it rains, the ground is wet, and the second verse, if it rains today, then we can draw the conclusion. No, we have the conclusion the ground is wet. Okay, so maybe you will think it's right because it rains and the ground is wet, and it's actually rains, so the ground is wet. So maybe we can see arguments. Okay, now write down some argument which is not valid on your paper. So you know when we call that argument, it could be valid or not valid. Right? So let's try yourself if you can write valid which is not valid. Write the argument. If the example just like this, so the argument is not valid. All right, maybe I am looking for someone who like summarize the definition for argument and valid argument in Chinese words. Oh, oh, could you summarize the definition of argument and valid argument in Chinese words?就是假设全部要是正，然后结果才会是正。如果假设是它导向的关系。Alright, have you finished your example of invalid argument? Have you finished it? You're not right yet. We need to take it to class. Right? Can you finish your example? Why it takes so long? Anyone finish your invalid example? Alright, you finish your example. Okay, please write your answer on the blackboard. It's okay to make mistakes. Okay, so thank you. So she gives the premises if it rains, then the ground is wet. The ground is wet. It rains today. Okay, so how do we make sure if the argument is valid or not? So maybe we can translate to positional logic first. If it rains, then the ground is wet. If the ground is wet, okay. So now she has the conclusion that it rains. Okay, so maybe we can see later if this is invalid argument because we haven't talked about yet. But let's see how we verify it. Okay, next we have the following definitions of argument form. Okay, so we can translate the proposition to different compound propositions or proposition of variables. Then we call that argument form. Just like our example, if we define rent by R and ground is wet by W, so we can rewrite the original argument to if R then W and R, the conclusion is W. Okay, so we call this argument form because we translate the original English sentence to compound positions or positional variables. Okay, next let's see how we verify if the argument is valid. The easy way is to use a truth table. So let's see. Okay, so let's say this example. If I play golf or tennis, this is the first premise. And the second one is if it is not something I play golf and tennis. Okay, so you can see actually I play golf and tennis Monday, Tuesday to Saturday. If it is Saturday or Sunday, then I don't play golf. So the conclusion is therefore I don't play golf. Okay, is that correct? I play golf and tennis if it is not Sunday. So I play golf and tennis Monday to Saturday. But if it is Saturday or Sunday, I don't play golf. That means we don't play golf if it is Saturday. So when I play golf, Monday to Friday, right? But the conclusion is I don't play golf. So that means this is not a valid argument because for the human purposes, we cannot draw a conclusion. So let's rewrite the premises and conclusion into the variables. Play golf G, play tennis T, Saturday S, Sunday U. then we can rewrite the premises in the conclusion to this conversational logic. Then we can verify by truth table. Okay, if all these premises are true, then we can draw the conclusion true. That's the definition of valid argument. So we can examine the truth table. Once the three premises is true, so we have all these cases that the conclusion is also true. So in this case, we can see for the fourth column, we have to be true for the premises that the conclusion is false. So based on this, we can see this is not a valid argument. Actually, we have three columns that gives premises are all true. So you can see the other two, the conclusion is true. But this one is false. So we can use the truth table to verify if the argument is satisfied by the definition of a valid argument. So based on the observation of this truth table, the given premises conclusion is not a valid argument. All right, so next, let's see. For valid argument, actually, we can simply consider the proposition. If the premises 1, P, 2, and they are all true, so we end them together, then we can, if this is not true, and Q is also true, if this is ontology, then we can call this is a valid argument. Okay, so we just rewrite the definition of valid argument to the form of propositional logic. Okay, next, we are trying to using different rules of inference to verify if the given premises is true, then we can draw the conclusion is also true. So you can consider maybe this is how we inference the conclusions. Next, we have a lot of different rules. So we will see these rules one by one. It helps us to develop our process, how to make the argument valid. Okay, the first one is modus ponens. Okay, so let's see. This is very intuitive and very easy. If the premises is P then Q is true, and we have the second premise, P is true, then we can imply, we can draw the conclusion that Q must be true. So this is right. Okay. So the rules is very easy because we have the conditional statement, and we are pretty sure if P then Q, P is true, then Q is also true. Okay, so the name of the rules is modus ponens. Okay, the second one, if P then Q, we know not Q is also true. So we know that the equivalent form of P then Q is contrapositive, right? If not Q, then not P. So we can apply the concept of modus ponens. If not Q, then not P, and not Q is true, then not P is also true. So maybe you can think of this, then you can see modus ponens is also true. But next, if you're familiar with this form, you can use it directly. You don't have to rewrite in P then Q, then not Q, then not P, and not Q, then not P. Okay, so you can use these two vectors directly to draw the conclusion. So we call this modus ponens. Next one, hypothetical syllogism. Okay, if P then Q is Q then R, then we can have the conclusion if P then R is also true. Okay, so if you don't believe it, you can verify this by the truth table to see it is a valid argument. Next one, disjunctive syllogism. Okay, if P or Q, not P, then we have the conclusion Q is true. So let's see. If we assume the premise is true, then not P is true, which means P is false. If P is false, P or Q is true. That means Q must be true. Then Q or false will be true. Right? So you can see this is definitely correct. All right, next one, addition. Okay, given P is true, then P or Q is true. Okay, this is okay, right? Because we already know P is true. No matter the truth value of Q, it doesn't matter. P or Q will be true. So we call this addition. Once P is true, then you can add another numbers by or the assumption to make this thing true. Okay, we have addition, so we have simplification. If P and Q is true, that means Q is true, and P is true. You can write P equals Q here. Okay, so this is how we call simplification because we need both P and Q is true, then P and Q will be true. Okay, so for simplification, actually you can remove the other variables and the rest is true. Next one, conjunction. Conjunction, if P is true and Q is true, then the conjunction P and Q will be true. Okay, this is very intuitive. Okay, last one, resolution. Okay, resolution tells us not P or Q R is true. P or Q is true. Q or R is true. Okay, maybe we can verify this quickly. If P is true, then not P is false. Okay, so now P is false, then R must be true, right? So if R is true, then the truth value of Q doesn't matter. Q or R is true. Okay, so for the second case, what happens for P is false? If P is false, then P or Q is true. That means Q must be true. So if Q is true, then the truth value of R, it doesn't matter because if Q is true, then Q or R will be true. So maybe we can verify this very quickly. The resolution, given these two premises, the conclusion is correct. All right, so next, I want you to remember this table because we will apply these rules. And you need to write down your steps and write down your reason. The reason is what of rules of inference is using to prove they are equivalent. All right, so maybe I think the rule is very easy, but the technique is a little bit difficult. Okay, so let's try to remember as possible as we can. All right, next let's see one simple example. From the given position, show that Q is a conclusion. So in this example, we have only one premise. P and P, P and Q. So we assume this is true, and we need to prove that the conclusion Q is also true. Okay, so let's see how we prove Q is true. If you see two terms added together, and this one is true, and then we can apply simplification, because simplification tells us if the premise is true, then P is true, and if P and So x1 is true, x1 is also true. And we can apply modus ponens, right? If P and Q is true, and we know P is also true, then Q must be true. So if you're familiar with these inference rules, then this one is very easy. Let's see how we write the steps. Okay, the first one is to write the premise P and P and Q. So this is step one, and the reason we write it here because it's a premise. So this is true. Okay, let's what is another truth? P and P and Q is true, and we can apply simplification to indicate that P is true. This is our second step. And step three, if P and Q is also true, because for simplification, you can remove either one, and the other one is also true. Okay, then based on step 2 and 3, if P is true and if P and Q is also true, then we apply modus ponens for step 2 and 3, then we have the truth that Q is true. So in this case, we have all the complete steps from the premise, and we get the final results, the conclusion Q is true. Then we complete the proof. All right, next let's see another example. So let's see, if it's not sunny this afternoon and it is colder than yesterday. So this is the first premises. Then we will go swimming only if it's sunny. So what's only if? Okay, so you can see we have no only here. And this is P, this is Q, right? But we have only if that means if you remember the definition. Okay. And then we don't go swimming, then we will take a canoe trip. If we take a canoe trip, we will be home on sunset. Then we need to prove that we will be home on sunset. Okay, do you have any indications this one is correct? But if it's not sunny this afternoon, and it's colder than yesterday, we will go swimming. If we go swimming, then it's sunny. If we don't go swimming, then we'll be no trip. Okay, so maybe it's not easy to verify by literal meaning directly. But let's try to rewrite this static argument, this argument to argument form. Okay, so we have the notation here. So maybe we can see the notation directly. The first one, not P and Q, R and P. Not R and S is S and P. And the conclusion is T. Right? So maybe we can trace back a little bit to see how we draw the conclusion. If the conclusion T is correct, that means we have the only connection to the conclusion is S and T. So how to make T is true? By modus ponens. If S is true, and if S and T is true, then we can have T is true. Okay, so we need another truth that S is true. How do we get S is true? If not R, then S. So if we have not R, then S will be true. So we need not R. How do we get not R? It's true. So we have the previous limits if R then P. So it's equivalent to if not P, then not R. So if we have not P, then we can have the truth of not R. So how we get not P? So the first premises tells us not P and the Q is true. So for simplification, not P is true. Now we calculate how we trace back from the conclusion to get the full process. Okay. So now we write it in the correct. Okay, the first one, we have the premise, not P and Q. Okay, so by this location, not P is true. Okay, now we introduce the second premise in R and P. So we have is R and P, and we have not P. So we can apply modus tollens, and that means not R is true. If you are not familiar with this, you can consider if we have not R then P by control positive, we can write if not P then not R. We have not P here, so we can use modus tollens to prove that not R is true. Okay, so you can use modus tollens or one additional step to apply modus tollens. Next, we introduce the third premise is not R then S, and we have not R. So we can apply modus tollens to indicate S is true. If S is true, S can be, then apply modus tollens again, and we can derive conclusion P is true. Is it okay so far? All right, let's see another example to see if you can trace back the conclusion backward to verify it is correct by yourself. So let's see the next example. If you send me an email message, I will finish writing the program. Okay, if you do not send me the email message, then I will go to sleep early. If I go to sleep early, I will wake up feeling fresh. Okay, so the conclusion is if I do not finish writing the program, then I will wake up feeling fresh. Okay, so it makes sense, right? Because you don't spend time writing the program, then you go to sleep earlier, then you will wake up feeling refreshed. So let's see how we rewrite this argument to argument form. Okay, the first one, you send me a message P, write program P, go to sleep early R, and wake up feeling fresh S. Okay, so if you send me the message P, then I will write the program. If you do not send me the message P, then I will go to sleep early R. If I go to sleep early, then I will wake up feeling fresh R and S. Okay, now we have all poses. The conclusion is I do not finish writing the program, then I will wake up feeling refreshed. Alright, so let's see, do we have any clue how we draw the conclusion? Okay, so we need not Q, right? So maybe we have if P then Q, and its good form is not Q, then not P. We apply control positive again. Not Q, then not P. Not P, then R. So what's that? If not Q, then not P. If not P, then not R. Okay. Remember incorrect, it's hypothetical syllogism, right? Okay, then we have not R, then S. Okay, so we can apply hypothetical syllogism again. If not P, then S. Okay, so finally we can make them all together to have not Q and S. Okay, so let's see the step. If we have if P then Q, so by control positive, we have if not Q then not P. Okay, then we use the next premise if P if not P then R. Okay, this one. Okay, so by hypothetical syllogism, we have if not Q then R. Because not Q can be for not P, not P can be for R. So not Q can be for R. This is one of the rules inference hypothetical syllogism calculuses. Right? And we use the last premise if R then S. So not Q then R, if R then S. By hypothetical syllogism again, we have if not Q then S. So this is the conclusion. Okay, so previously we have seen all inference rules combined with some equivalent fact we already know in maybe section 1.2 or 1.3 contrapositive. Then we can combine all this to draw the steps one by one. Next, we will see the rules of inference for practical logic. If the statement is quantified statement, what kind of rules of inference we can use? If we have for some, okay, how do we draw the conclusions based on practical logic? Okay, the rules is very easy. The first one is universal instantiation, UI. Okay, so if we have the premise for all x p of x, then you can find the instance within the universal. P of C is true. Because for all elements, for all x p of x is true, then of course you can draw any instance C that P of C is also true. So we call that universal instantiation. Okay, maybe we can see this example. If we have the domain of all dogs, the field is one dog. Okay. Then we have the for all experience, all dogs are covering. Then field is also covering. Because field is one dog of one domain. Right? What is covering? Coloring means you can lean forward that objects you can stay together. So that means you can hold your dog and lay down your dog, and that is called cuddle. Okay. So usually who we cuddle with maybe our boyfriend or girlfriend, right? Okay. So that's cuddle. So that means dogs are very furry, very cute. So we like to lean forward to the dog. Right, next one, universal generalization. Okay, so let's see if the premise is true for PC, for arbitrary C within the domain, then we can draw a conclusion for all XP of X is true. Because C is arbitrary elements from the domain. If you choose anyone, whether you choose anyone, P of C is true. That means for all XP of X is true. So once I see the arbitrary elements, then we can apply universal generalization to generalize for all x of x. All right, next one, existential instantiation. For some x of x is true, then we must find the particular instance of C for some x, because it is already obvious for some x of x is true, and we can draw that particular element of C is true. So we call this existential instantiation, because you can find out what instance we call this EI. All right, last one, existential generalization. If this is true for some under C, then we can write for some x p of x is true. Okay, so we have only 4 rules for inference for practical logic. Next, let's see how we apply these inference rules to prove that valid argument. Alright, so we have seen this example before. John Smith has 2x is our conclusion. And we have a sequence of premises. Every man has 2x. John Smith is a man. So John Smith has 2x. Okay, we know it's true, but here we want to know how to apply rules of inference to prove that it's true. Okay, so first one, every man has 2x. So we use m of x to indicate x is a man. A of x has 2x. Okay, so from the first premise, we have every man has 2x. For all x is a man, then it has 2x. Alright? So if we can see this is correct, then we can see John Smith is one example. So if John Smith is example is J, then we have if MJ, then MJ. If John Smith is a man, then John Smith has 2x. So this is universal differentiation. Because we know for all x cases is true. If John Smith is one particular element within the domain, so f of J is true, then f of J is also true. Right? Next, John Smith is a man, that means m of J is true. Okay, so now we have m of J is true. If m of J is true, then we can apply Mulder's pollens to have the conclusion m of J is true. Alright, so maybe by its literal meanings, we know this is correct. But now we have a formal step to prove that the conclusion is true based on inference rules for practical logic. Next, let's see another example. We have the premises. A student in this class has not read the book. Everyone in this class passed the first exam. So the conclusion is some class who passed the first exam has not read the book. Okay, so this is correct, right? Because one student has not read the book, a whole student passed the exam. So that student passed the exam, but he hasn't read the book. So by its literal meaning, it's correct. But that's how we prove this by rules of inference. Okay, so let's see the notation. C of x, x is class. P of x, x has read the book. P of x, x has the exam. Okay, so let's see first premise. A student in this class has not read the book. So we have for some x, x is a student, but x has not read the book. We have such exists. X exists. And everyone in this class has passed the first exam. For all x, if he is a student of the class, then x passed the first exam. Now we have the conclusion. Some student passed the first exam and has not read the book. So for some x, p of x, and not p of x. And I believe this is for you right now, but the next book is how we apply rules of inference to prove the conclusion based on the given premises. Okay, so let's see. If we have the first premise for some x, c of x and not B of X. So we can apply existential instantiation. For some X, it's follow the property. So we can do that particular element C, or here we use A. So this element A has satisfied the first we have this two, and you can see this is N, right? So we can apply simplification that C of A is true. Let's see the second premise for all x C of x then P of x. So we use the same element A because in this domain everyone satisfies this property, even if for A. So if C of A, then P of A. Okay. Right now we have if C of A then P of A, and we also know C of A is true. That tells us by step 3 and 5 we can apply modulus ponens to indicate that P of A is also true. Okay. Then what we need is for some x P of x and not P of x. So now we have P of A, but where is not P of x? Okay, by the second step, by simplification, not P of A is also true, right? So here we have not P of A. For step 6 and 7, P of A is true, not P of A is also true. So we can combine them using conjunction. Okay, this is true, this is true. And both them and together will be true. This is the rule of inverse conjunction. So we know P of A and not P of A is true. And then we apply existential generalization. If we can find a particular element A, then we can write for some x P of x and not P of x. So this is how we draw the conclusion. Okay, so actually we have only 4 rules for rule of inference for phenomenology. Actually, when we run the 4 steps, we need to combine with the rule of inference for all right. Any questions so far? All right. Next, let's go back to a simple example. We have seen this Socrates example many times. For all x, if x is a man, then x is immortal, and Socrates is a man, so Socrates is mortal. So now it becomes very simple for us to prove it is true, because for all x, m of x and mortal of x, this is our premise. Then we can apply universal instantiation to find a particular element. That element is Socrates. Socrates is a man. So if Socrates is a man, then Socrates is immortal. And by the second premise, Socrates is actually a man. So we have step 2 and 3, and we can apply modus ponens to indicate that Socrates is immortal. All right, next one, universal modus ponens. Okay, for all x, if P of x is true, then Q of x. Then we have P of A. A is a particular element in the domain. Then we can infer that Q of A is also true. So it's very easy, right? Because for all x, P of x is true, then Q of x. And we know the element is A. A is in the domain. So P of A and Q of A is true. If we have the condition statement and we also have P of A, then of course Q of A is true. But you don't have to extra steps. What is called universal modus ponens. This directly, then you can draw the conclusion Q of A. But if you don't remember this, it's okay, because you can also apply reversal instantiation to find P of A is true, then P of A, and P of A, and P of A. All right, lastly, let's see our ultimate example, Superman example. So let's see how we prove this is a valid argument. Okay, next, if Superman is able and willing to prevent evil, he would do so. If Superman cannot prevent evil, then he is impotent. If he's not able to prevent evil, then he's malicious. We can also say it is very mean because he's not willing to prevent evil. And we know that Superman does not prevent evil, so it's also a premise. So if Superman exists, he's neither impotent or malicious. Therefore, the conclusion is Superman does not exist. Okay, you can see we have a lot of premises here, and we have the conclusion Superman does not exist. Next, let's rewrite this sentence to propositional variable. Okay, so this is our argument. If Superman is able and willing, then he will prevent evil. So we use A to indicate that is willing. A is able to prevent evil. W is willing to prevent evil. Then if he is not able to prevent evil, then he is impotent. If he's not willing to prevent evil, then he's very weak. And we know Superman does not prevent evil. Okay, so if Superman exists, he's neither impotent nor weak. So now we have all this here. And the conclusion is Superman does not exist. Alright? So after we write the English sentence to propositions, then let's see how we draw the conclusion from rules of inferences. Okay, so maybe we can apply our trick a little bit. If we want to draw the conclusion, how we trace back a little bit to find the connection. If we want to prove that E, okay, so we can see only connection is 5. Right? So we have if E, then this one. So how we get not E? So if E is the last step, that's our conclusion. So the way to get not E, by all these premises, we must have not I and not N, then not E. Right? This is the only way we can get not E. So if P then Q, then not Q and not P. So we can get not E here. Okay, so maybe we can rewrite this a little bit because we can apply the Morgan's law here. So not parentheses something, so we can write I over N implies not E. Right? Okay, so now we have this one. So how we connect this one to this premises? Because currently we have not P and not W then N, not A then I, and W then E. We don't have anything I or N and not E. Right? Because so we cannot trace back. So how about we start from our premises to see if we can write something here, then we can derive this step. Okay, so next let's see what we can do by this. Then we can come back to this. Okay, so this one we used before. So how about 1, 2, 3, 4? Which one you will start? apply rules of inference. Okay, so if you watch it, you will see we have not P here. Right? We have not P, then we have A and W, then P. So what is this? This is modus tollens, right? So if you have P and Q, and you have not Q, then we can imply not P. So this is modus tollens. So maybe we can stop here because it's the easiest one. Okay, so we have the step one, the first premise A and W, then P. This is the premise. You write the reason by yourself. Okay. And the second step, we have not P. Okay, so the third step, based on 1 and 2, and we can apply modus tollens. So we have not P and W. Okay, then we can apply the modus law a little bit because we have the parentheses and not. So the first step, not A or not W. Right? So that's the results we apply premises 1 and 4. Now we have two premises left here. So maybe we can see. Because we have not A and not W. And we have not A here, not W here. So maybe we can choose anyone to connect with this one. So maybe we try first. Okay, so for the fifth step, if not A, then I, how do we write it? If P and Q, then we have not P or Q. So we have A or I. Right? So this is my propositional logic. It tells us it's equivalent form. If not A, then I, then we have P then Q, not P or Q. So we have A or I. Now watch the step 4 and 5 closely. We have A or I, and not A or not W. What's that? Because we have A or something, not A or something. Okay, so if you don't remember, then let's go back to resolution. Okay, if P or Q and we have not P or R, resolution tells us Q or R is true. Okay, so now we have A or I, not A or not W. By resolution, we have I or not W is true. Okay, now we have only one left. Okay, we have the third premise is not W, then okay, so by and for the seventh step, if W then M, so we can write to W or M. If P then Q, then we can write to not P or Q is also true. Okay, this is by propositional logic. Now we have step 6 and step 7. Okay, we have W or N, and we have not W or I. Okay, so we can apply resolution again because we have W in not W or something. So by resolution, we have N or I is true. right? So once we have M or I, then the problem is solved. Because originally we have not E, and we know if we have not I and not A, then we can get not E. And this one is equivalent to I or M. Okay, now we have I or M. So this is means I or M, then not E. So this is our nice, this is our nice. So we have if not I or M, then not E, and we also have I or M is true. So we can apply modus ponens to indicate that E is true. All right, so maybe you can write this step, but uh, we don't have to follow this step exactly. You can write your own step. Which one goes first? Which one goes later? It's okay. Once you can make all this make sense, then you can go to conclusion. It's okay. All right. Let's see any question for this example. Can we repeat by Chinese again? 好，那如果没有问题的话呢let's see how our homework assignment. Okay, so we have 1.4 to 1.6. So we have the question here, and the due date is 2 weeks. No, it's Wednesday. All right. Any questions so far? If no question, we will go to the exercise. Any question? Okay. So if no question, then I will ask for the last exercise. Please prove it a valid argument by choosing people. You have 10 minutes for you to complete the exercise. Because I'm trying to help you. If you have seen this question in examination and you don't know how to write the full process of this, at least you can try to prove a valid argument by truth table, right? So I'm saving you. Okay? So let's see how to prove this valid argument by truth table. So let's go back to the example of the truth table. So you need to verify by the truth table if all premises are true, then you will get all results are true. And you can say it's a valid argument. All right, so I switch the pages to this one. Okay, if you don't do the truth table right now, you will do it in the midterm examination. So you must do it once. he's calculating how many rows in this truth table. Maybe you can tell everyone your results. What's the number of rows in this truth table? How many? How many rows? 30, 32. Is that right? 32 is not a very large truth table. Because I'm not doing this. That's the exercise. You can choose to do it right now or leave it to midterm examination. It's up to you. Okay, can you tell me how many columns of this truth table? Let me choose someone to calculate it for us. How about you? How many columns in this truth table? All right. Is that the answer? Are you sure? 16? Maybe you can tell us why it is 17. Please come forward. Face to everyone. How you calculate 17? Use your microphone. 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. Calculation. Do you want to do it again? Okay. So maybe how about you do this because you're saying it's he's saying it's all right. Please. How does calculate how many columns? Please come forward. Because the way he is calculating the number is not very regular. So let's see how you calculate the rows, the columns. Microphone, please. You are missing the variable. If you calculate the variable first, you are missing one variable. Okay, so you have six variable. Okay. No. Let's calculate to the end. You have six variables, and then okay. Let's try your answer. Please. Okay, now it comes 19. How about you? 18. Is 18 correct? 18 correct? Really? Okay, so it's 18. Okay. Okay, so I hope you can finish the exercise because we have different ways to prove the valid argument. So by rule of inference, you need to remember a table of so many rules, and then maybe you can use truth table. Okay, so any questions last time, last chance? I don't know. Mm. Mm. Okay. Okay, if no questions, then we call it a day. So see you next week.
你知道我刚刚以为1点半才上课，然后我速度打完，然后15分发现，那个快点打我，然后我飘过来，相当我，我都把手机变成小的，特别大，那不是都是8个，现在都是8个。好，我们觉得这个。我今天晚上没事，人家打我，再次打我。分解几个？多的不用马上去找一下啦，我先看看这个。我自己前面不表还是没有把它拆出来，就是大它就是前提列，然后不知道看过吗？